Some of the other stuff that we are interested in as far as functions would be any sorts of things that can change the way that they appear that are linked back to parts of the equation of that function. So we're going to start out here with our basic sorts of shapes for things that we can reasonably deal with at this moment, and we will be able to take the transformations we're going to discuss and apply them to other kinds of functions that we might encounter later. But we've got our basic linear function, our basic quadratic function, our basic cubic function. We've got our basic square root function, our basic cube root function, and our basic absolute value function. Now, the kinds of things that we can do, we're going to talk about one at a time. So let's start with the two that are the nicest for us to represent if we are graphing things. And that would be any sort of shift that takes place either up or down, and any sort of shift that takes place to the left or to the right. Now, there are two different kinds of shifts, and so there are two different things in our function that we should be looking out for. We're going to use the absolute value function as our basic function here for many of these because it's a nice little shape for us to work with, and it's got that very distinctive point on the V. So if we talk about either adding or subtracting a number outside of our original function, so here's our original function, absolute value of x. Anything that is added or subtracted outside, it could be out at the back end, usually, but it could be out at the front end. So -2 plus the absolute value of x, same as this example here. If we are subtracting, as we see in this example, we're going to move down. Whatever number we're subtracting is however many clicks we move down. If it was adding instead, well, the opposite of down is up, so we would shift up. So subtracting 2, click, click, move down 2 units. The whole entire picture is moved, shifted down, or alternately again, shifting up. If we take that idea of adding or subtracting and say, well, the other place that it could be, rather than out at the front or out at the back, outside of the original function, it could be inside of that original function. So inside of the absolute value bars, if we have adding or subtracting that's taken place, then there's going to be the other kind of shift, either to the left or to the right. This one is, if we are subtracting, we go to the right. If we are adding, we go to the left. And for a moment, you might say, that's a little counterintuitive. I thought that, to the left is negative and to the right is positive. So if we're subtracting, shouldn't it be? Why is it? Here's where that V point actually comes in rather handy to us. The basic graph has the point of that V where x is 0. If we change what is inside of the absolute value bars, then we are going to change where that V appears. If we are looking at what's inside of that absolute value and saying, well, where would this now be 0? Where is x minus 1 equal to 0? Well, that's when x is equal to positive 1. That's the positive that is telling us go to the right. So when we backtrack it, it actually changes what you might have expected based on shifting up and down. If we have x minus a number, shift right. If we have x plus a number, shift left. The other kinds of transformations that can also be relatively quick to identify are the ones that have to do with reflecting. So that's the math language, reflection about the x-axis, reflection about the y-axis, side to side versus up and down. If we have a negative that is out in front of our basic graph, basic function, then that's going to be our reflection about the x-axis. The original y values get changed to the negative versions, the opposite versions. Conversationally, flip that sucker upside down. If the negative, however, is inside of that basic function, now we can't see this with the V shape, because if you take that V shape and then you do a reflection about the y-axis, if you are going to spin left to right, then we're not going to be able to tell the first V shape from the second V shape. So we switch to a shape where we can see that there is that difference. Our square root function has that kind of curvature to it. Starts at the origin, curves off to the right. If we take that function and instead of just a regular x, inside of the inside of the square root, we put in the negative, what's that going to do? Well, in order for us to have things that we're allowed to plug in, we're going to need to offset that negative. So we're still going to be able to plug in 0, that's okay, but we're not going to be able to plug in a positive 1 because we couldn't have the square root of a negative 1 showing up in our grid. So we're going to have to instead plug in negative numbers to offset that negative that's already in there. And that means that instead of our graph going off to the right, we're having to spin it around, and it's going to have to go off to the left. So as long as we can recognize those basic sorts of functions by their rule, a squared, a cubed, an absolute value bars, a square root, cube root, then hey, we can tell where is any of the adding or subtracting. Is it inside or is it outside? Where is the negative? Is it outside or inside? We'd be able to tell those sorts of things. So out of the shifts and the reflections, those are the nice ones. But there are other things that we can do and we can say, and this is a little bit more difficult to be as detailed about these, but the other ones that we have are stretches and compressions. So let's go back to that V shape again and say, what's going to happen if we, instead of adding or subtracting, instead of throwing in a negative, if we incorporate something like multiplying? Multiplying by something bigger than 1 versus something between 0 and 1. Where do we do the multiplying? Is it outside? Is it inside? How do these kinds of changes to our function rule, our function equation, I can't use the word shift, how do those carry over to what happens in our graphs? So as it happens, if we have a number that is outside of our original function, that is going to be related to vertical, stretching or compressing. A number bigger than 1 would be a vertical stretch. A number between 0 and 1 would be a vertical compression. Correct? If then we take those numbers and put them inside of our function, we notice that there was that kind of switcheroo sort of thing happening with the shifting. Notice that switcheroo also happens now with the stretch and compress. If we are multiplying by something bigger than 1, it's not a horizontal stretch. It's not just change the word vertical to horizontal. It switches around the manipulation as well. So instead of vertical, it's horizontal. Instead of stretch, it's compress. It's this whole switcheroo that happened. Again, that has to do with how do we take something in the original function like a 1. Now we've got 2 times x. Instead of plugging in a 1, well, 2 times x. How do we get that same 1 coming out? Well, it's going to be plugging in an x equals 1/2. X equals 1/2 is closer in. So instead of x equals 1 farther out, x equals 1/2 closer in, we're squishing horizontally. Horizontal compression. If we're talking about a number between 0 and 1, horizontal stretch. So we've got those shapes mapped out with the color coding. It's a lot harder to say what specifically we're talking about with the stretch or the compress unless we've got something really convenient like a 2, a 1/2, maybe a 4, and 1/4, a 3. Hey, instead of double, triple, okay, cool. But like, there are lots of other numbers that we could have show up. That'd be a lot weirder to try to talk about. What's going to happen if we throw a 7/5 out in front instead of a 2? Well, it would still be a vertical stretch, but beyond that, we don't have a nice description. Oh, what if we threw in, a 3/11 instead of a 1/2? Well, instead of being able to say, oh, we're just going to compress that sucker in half, that'd be a lot weirder to talk about. So we usually just stick with this really generic kind of description. We have a vertical stretch. We have a vertical compression or a horizontal. We don't really go into more detail like we would about shift left so far, shift right so far, shift up, shift down. We can be specific about those. We can be really clear cut. And that's not as easy to do with the stretching and compressing sort of manipulations. So, we do what we can. What this means for us then is that all together, we can have a list of these comments about how things are going to have to work and kind of a generic version of what things look like here. So if we've got our original function and there's stuff going on inside of it, what does that come back to? That comes back to any kind of shift left or right. That comes back to any kind of horizontal stretch or compress or spin left to right. Anything that has to do with a horizontal element. Anything that's outside of the function, out at the back, for instance, is a common place for that to happen, adding or subtracting. Out at the front, with multiplying, those sorts of things are going to have a vertical manipulation happening, whether that's shifting up or down, whether that's vertical stretching or compressing, or the flip upside down sort of a thing. So let's take a look at some examples where we can see these sorts of things happening in actual functions. So let's start with this function f of x equals 3 square root of 2x minus 4 plus 1. Notice the pause there after the end of that square root. Gave a nice little pause before I said the plus 1. It's one of those things when you're talking about stuff so that there's hopefully less confusion with people hearing things. But what we've got is not a very friendly version of that function if we are trying to figure out what kind of transformations are happening, if we're trying to describe the transformations that are going on. Oh, the 3 out front is fine, the plus 1 at the back is fine, but what's inside of that square root is not as nicely usable for us. So we want to rewrite that. we say, oh, you know, that's not just a regular x that's in there. It's got a 2 out front. Let's make sure that we go ahead and factor the 2 out of everything that's trapped inside of that basic function, that square root. Factoring out a 2 gives us this parentheses x minus 2. So the things that are different versus our regular square root of x, we've got a 3 out in front. We've got a times by 2 inside. We've got a minus 2 inside the square root, inside parentheses. We've got a plus 1 at the tail end. The nice things for us to deal with are any kinds of shifts, because what we are usually going to be seeing is stuff that is clearly adding or subtracting on the outside. Hey, there we go. Let's go ahead and tag that. Adding or subtracting on the outside would mean we're going to have a shift up. Because it's a plus 1, that's a shift up 1. We can be specific. We don't just stop at saying shift up. We can be specific. We say shift up 1, because that's a 1. Inside those parentheses, we get the x followed by the minus 2. Because we've got the x followed by the minus 2, that means that we've got a shift right 2. We have to remember that any of the stuff that is directly tied in with the x has that kind of switcheroo sort of thing happening. So, oh, a minus, that's not left. Switcheroo that's to the right. Shift right 2. Well, those are the nice ones. And the other ones, those are kind of those weirder ones. I wouldn't necessarily want to try to be specific about what the 3 itself is doing beyond some sort of vertical stretch or compress. What is the 2 doing beyond some sort of horizontal stretch or compress? How did I know it was vertical for the 3 and horizontal for the 2? The 3 is all the way out in front of that basic square root. Stuff that is out front, all the way out at the back, those are vertical manipulations. Stuff that's tucked inside of our function, so that's the square root function, that's tucked inside, that's going to be horizontally related, so that's a horizontal. Timesing stuff, that's a stretch or compress. So we would have to say, what's this stuff going to do? Well, the nice one to keep track of, at least in my opinion, is the vertical stuff, because that one makes sense. If I times by 3, out in front, stuff gets bigger, stretched. That makes sense. And then I think about the switcheroo, the stuff inside. Oh man, times by 2, I usually think that's bigger, but I got to remember that's a switcheroo because it's tucked inside of that function. So instead of getting bigger, it's getting smaller, it's getting squished. That's going to be a horizontal compression happening with that one. And again, we're not trying to be more specific about things. As far as the vertical stretch and the horizontal compression, we're just saying, hey, look, we at least got a basic idea of what those are going to be doing. We don't have to be more specific. That's when we can actually start graphing things either by hand or with a graphing tool, like a graphing calculator. So good enough to recognize that that's happening. We have maybe an idea in our head, oh, that square root, what's that looking like? That's got that kind of shape. So if I shift it up 1, if I shift it to the right 2, if I vertically stretch it, that's kind of wrenching that up like that. And then if I am horizontally compressing it, that's going to kind of wrench that back and create this more curved kind of shape versus the basic square root without any of those extra bells and whistles. We don't always have to rewrite things. We read this next example here. G of x is equal to negative parentheses x plus 3 parentheses squared plus 4. parentheses squared, hey, that's just a like basic version would be x squared. So what stuff is new? Well, I got the parentheses, so that's definitely something I got to worry about what's happening. I got the plus 4 that I heard at the end, and I got the negative that I heard at the very beginning. Well, I'll have to rewrite things in this case. I have those key features that don't appear in the basic function. I need to know how those are going to change my basic shape. So instead of the x squared, what's the plus 4 going to do? What's the plus 3 going to do? What's the negative going to do? We're doing them in that order again because it's always nicest for us to take care of stuff that's completely outside with the adding or subtracting, because that's going to be very direct. Add, vertical shift up, subtract, vertical shift down. So that's a plus 4. That's going to be a shift up, 4. Then looking for stuff that's inside of our function, so inside of the squared, that's going to be that what's inside the parentheses. That's a good thing for us to keep an eye out for. Not an always sort of thing, but a lot of times sort of thing. We'll have parentheses helping us, hey, x plus a number because of the plus and the switcheroo. That means instead of to the right, that's to the left. The switcheroo to the left instead of plus. We're going to shift left, specifically 3. And that leaves us with that negative out front. Again, that negative out in front. Stuff that's at the very, very front. Stuff that's added or subtracted. Also outside. That's vertically related. So the negative, vertically related, what are we talking about? Oh, we're talking about that reflection business. Or if we're being more plain spoken about it, we're going to flip that sucker upside down. So that negative, we're going to flip that shape upside down. So we talk about that x squared being our basic shape. X squared, do a little fun dance, right? Shift up 4, so click, 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 click. Shift to the left 3, click, click. Doesn't change the shape itself, just changes its location. And then we've got that negative, and that's going to go foomp, flipping that sucker upside down. You can dance if you want to. You can leave your friends behind. But again, there is that possibility that we need to rewrite things from the way that they originally appear in our function. And sometimes we have to do more rewriting than others. At first, not a big fan of what's going on underneath that cube root. Cube root is going to be our basic function. Don't like that because that kind of changes this order that I expect things. I expect x stuff to be followed by pluses and minuses. I expect the x stuff to show up first. So there's that very kind of obvious way of saying, well, if this is what I normally see, well, I'm going to go ahead and just change that. Then there's the more annoying side of this. We like that x to be by itself, not having the number out in front of it, not unless we're going to have some parentheses show up. Well, to get parentheses to show up, we got to take that negative 1/3, and we've got to factor that. It's still going to stay underneath of the root, but it's going to get factored away from the x. So that's going to change what we have appearing after the x. With that factoring happening, again, we can think of this in a sort of backwards multiplication sort of idea. If I'm factoring out a negative 1/3, negative times what gives me a positive? Well, negative times a negative. 1/3 times what number gives me a 4? Oh, it's got to be a 1/3 times 12 gives me a 4. Now we can talk about what's going on. And again, the nice things for us to pick out, we've got that -2 that's showing up outside of our square root, or excuse me, fourth root. We've got in the parentheses this -12, this x minus 12. Then we've got inside of that root, so still horizontal elements, we've got a negative and we've got a 1/3. So start with the nice ones, the shifts. And the shifts are going to be based on the blue and the green. So shift down 2, shift right 12. Then we've got the negative. That's the next nice thing to take care of, because that negative is inside of that root. That negative is going to have an impact on the horizontal stuff. That's a reflection. Again, if we wanted to be fancy about it, we're going to reflect about the y-axis. But if we want to be more plain spoken about it, we're going to spin left to right. Or right to left. I mean, it doesn't matter. You're still spinning rather than flipping. So spinning left to right, taking that shape that we've got and spinning that. Then we've got that 1/3. We go, oh, 1/3 is small, but wait, the horizontal stuff has that switcheroo, so instead of small, switcheroo that and go big. That's going to be a horizontal stretch. And somehow or another, I went from a cube root to a 4th root. That's terribly annoying to have noticed at this stage. So, whoops, we're going to have to fix that. There we go. So cube root doesn't change the transformations, but it does change the shape that we would start out with. The 4th root didn't show up in our basic list, so we won't worry about that. We could expand, but we won't worry about that at the moment. We'll worry about those fancier roots later on. Cube root. So that's got a bit of that kind of snaky shape. And if we're talking about shift down 2, shift to the right 12, all the way up to the right, all the way over there, and then spin left to right. Now, that's right hand, that's going up and to the right. When we spin, that's going to be going to the left and up now. Going to the right and down because we spun. And then stretch, oh man, so instead of this kind of snaky bit of curvature to it, by stretching it, we're flattening that kind of curvature out. We don't know how much we're going to flatten it out because, again, we're not really trying to spell out in greater detail what that stretch is going to do, but because of that shape, stretching that kind of snaky looking S shape will flatten it out. Stretching it horizontally, that will flatten that out a little bit. You can confirm those sorts of things by actually using your graphing calculator to graph each of those